Okay, thank you, Martin. So hello, everybody. Thank you for being here. So today, as Martin said, I will talk about how to hamper the effect of Earth structure approximations on Onfault deformation estimates. So what I will present today is a collection of several studies that have been made in collaboration with Mark Simons and Eric Fielding from Caltech and JPL, Anthony Quentin and Olivier from here, and finally Leah Longer and Jerome Trump from Princeton. So first, what I mean by unfold deformation is mostly slip. So it can be coseismic slip, it can be post-seismic slip, it can be interseismic slip. So in this case, we rather speak about interseismic slip deficit or coupling, but it can also be rupture, so in a kinematic sense. Today, I will mostly focus on the slip, but I think most of my conclusions will be true for the kinematic rupture. So first, how do we estimate the unfold deformation? If you look on the left, you have a representation of the reality. So you have, for instance, an earthquake that occurs on a fault. Fault is complex, the medium is complex, and the deformation that occurs on the fault will produce a displacement at the surface. We measure the displacement with data. This data can be GPS, INSAR, or seismometers, for instance. What we do to estimate the unfold deformation is to make an approximation of the reality. So we make an approximation of the medium, an approximation of the fault. For instance, what I do here is to consider a planar fault geometry. We'll divide this planar fault into very small pieces that are called subfaults. And the first step to estimate this deformation is to solve the forward problem. So to do that, we find or we look for the displacement at the surface that is produced by a small displacement on one of the subfaults. Once we have done that, we can solve the inverse problem. The idea to solve the inverse problem is to find the model that will explain the displacement that we observe at the surface. To do that, the idea is to minimize the residuals between the data, so our measures, and the prediction that we make at the surface. At the end, when we have solved the inverse problem, we end up with something like that. So the rectangular shape that you can see here. So this is the fault. Every small square is a subfault, and the color corresponds to the amplitude of the deformation on this fault. So we can wonder why we estimate this on-fault deformation. So we all know that the deformation on the fault is very complex, both temporally and spatially. So we want to estimate this complexity to better understand the generic earthquake properties or the generic fault behavior. We want to also improve our understanding of regional tectonics. For instance, we want to understand why some part of the faults are slipping aseismically without producing any earthquake, or why some other parts actually produce earthquakes. The other thing that we want to understand better and maybe to prevent is seismic and tsunami hazards. And I'm showing you an example here from the USGS Earthquake Hazards Program. So they are providing estimates of seismic and tsunami hazards in almost real time. So here is an example for the Ridgecrest earthquake that occurred 2 years ago in California. So within a few hours after the earthquake, they are able to provide a seismic slip model. And from this slip model, they can predict a map of the shaking around the epicenter. And from the shaking map, they can also predict the economic losses that will happen after this earthquake. So what I think is very interesting right now is that it seems that everybody almost believes that what we are currently able to image, so the slip models, is very close to the reality, or at least is a very good approximation of it. The issue is that after every earthquake, we realize that we are not able to converge towards a unique or at least a coherent solution. That's why I wanted to speak first about the Ridgecrest earthquake. I think this is a very nice example of the issue that we have with coseismic slip models. We are not able to get a unique solution. So that's what you can see here. So there have been a lot of models that have been published for this sequence, sorry. And one interesting thing is that they are all very different. So they are different in the location of the maximum slip that has been inferred. For instance, here you have one main slip patch here as well. And this model, we have two main slip patches, etc. And also another thing that is interesting is that the amplitude of the slip that has been inferred is very different. Here, maximum amplitude is 4 to 5 meters, and here, for instance, is up to 10 meters slip. So this is a very good illustration of the ill-posed nature of the inverse problem when we try to solve for the slip. What this means is that there are a lot of different solutions that can explain equally well our measures at the surface of the Earth. And this is even worse when we consider all the possible sources of bias that can impair our ability to model the Onfault deformation. So there are three potential sources of bias. The first one is the data. So data have noise, and this noise can be transferred to the space of our model. Another source of bias is the inverse problem. I already told that there are a lot of solutions that can explain our data at the surface. So the way we will try to find this solution will impact the results. And finally, the last source of bias is the way we solve the forward problem. So all the approximations that we'll make will impact our results. So today I will mostly concentrate on this third source of bias. So if we go back to the Ridgecrest case, we had several seminars at Caltech talking about this sequence. And in one of them, a USGS geologist was presenting a very, very similar slide. And she was asking something like, how can we trust all of these models if they are that different? I think this is a very, very good question. But I also think that we can maybe reformulate this question into the first question, which is, are these models really that different? And a second question, which is, if they are really that different, then why? So I will try to answer to this first question. Are these slip models so different? First, I would like to say, no, they are not so different. I'll try to explain what. So I told you there are a lot of different solutions that can explain our data at the surface. That's very hard to image all of these solutions. That's almost impossible because there are a huge number. So what we do usually is to decrease the number of solutions and to minimize the size of the solution space. To do that, one of the most widely used technique is to regularize or smooth the models. The issue with that solution is that it is not physically justified, and also it has a huge impact on the solutions that we get. For instance, here you have a study by Mathieu Cos that has been done 10 years ago. So they consider a slip model, so they calculate the displacement at the surface that is caused by this model, and they try to infer back their slip models, but using different regularization parameterizations, sorry. So you can see that if you use different smoothing values, then the slip model that you image is very different from the reference model. So what I want to say is that maybe all these models for the Ridgecrest earthquake are actually very similar, but they have just been inferred with different regularization or smoothing values. One way to overcome this issue is not to regularize the problem and not to minimize the exploration of the solution space. We can do that by using Bayesian approaches to sample the solution space. So here is a very basic representation of a 2D solution space to explain very quickly what Bayesian sampling methods allow us to do. So in gray here, you have the residuals between the predictions and the observations. So that's what we are trying to minimize when we are solving the inverse problem. When you are using very basic probabilistic optimization approach, such as a least square, for instance, you are looking for one minimum. So very often you are finding a local minimum, and if you are lucky, you are finding a global minimum. When you use Bayesian sampling methods, the sampling of the solution space is driven by probabilities. So very often you are able to sample all of the most probable models. So that's what is shown in orange here. So at the end, you end up with all of the most probable models of your solution space. And this set of samples also allow you to estimate the posterior uncertainty on the parameters. So that's very nice. So all of the results I will present you are based on these kind of approaches. So if we go back to this slide, um, if we consider that, we consider that this hypothesis is true, so that all of these sleep models are actually very similar, and the only thing that is changing is the regularization or the way we solve for the inverse problem, then we could say that let's all use the Bayesian inverse methods, and all of the methods will converge towards a very coherent solution. Actually, that's not so simple. That's what I want to show you here. So here you have a sleep model, again, for the ridge-race earthquakes that have been inferred by Hamini and that have been published last year. And in this model, so they use INSAR data and GPS data to constrain the sleep on the fault, and they also use a Bayesian approach to solve for the sleep. In the bottom, you can see sleep models that I did with exactly the same data and with exactly the same inversion approach. However, if you look at the amplitude of the sleep, for instance, here the maximum amplitude is 10 meters, here it's 10 meters as well in red. The location of the maximum sleep is different. It is shallower than in the sleep model from Bahamin. And also in this part of the fault here, you can see that I image shallow sleep, large values of shallow sleep, which is not imaged here. And for instance, the Bahamin image is some sleep at depth here, which is not present in this sleep model. And actually, the only difference between these two models are the assumptions we made about the Earth's physics. So about the fault geometry, about the way we parameterize the problem, about the crustal structure, and about the uncertainties that we considered. So the other answer to this question is yes, all of these sleep models are different because of the way they were regularized first, but also and mainly because of the approximation and simplification of the Earth structure that have been made. So what we could say is that all of these solutions are conditioned by our prior choices. And what I will try to do in the following talk is to convince you that we have to be very careful about how we model things and about our assumptions. And one way to be very careful about that is to consider uncertainties. So as Martin said, during my PhD, I worked already on, about epistemic uncertainties. So epistemic means that it stems from our approximation of the crustal structure. So I will just briefly remind you how we can account for epistemic uncertainties. I will then present nice study that we did last year by accounting for epistemic uncertainties. So we'll show you what we can do. And then in the next part of the talk, I will focus on two effects that are very often widely neglected, the topography and the 3D elastic structure. So first, how do we account for epistemic uncertainties? I will be very quick about that. What we do is we estimate the sensitivity of surface displacements to a small perturbation of the medium. So what I did during my PhD to look for epistemic uncertainties due to variation in the fault geometry, so I will use that to explain. So if we look at the uncertainty due to variation in the fault, for instance, what we do is to take one fault geometry, calculate the displacement at the surface, and just slightly vary this fault geometry, so here this fault deep, and calculate again the displacement at the surface. And what we do is to look at the evolution of the surface displacement. From this evolution, we can define the sensitivity of the surface displacement and incorporate this sensitivity directly into our inverse problem, as if this sensitivity was kind of noise or errors in our data space. So the main findings of my PhD were that yes, of course, we need to account for uncertainties, otherwise our results can be like biased by a lot. I will not stay on this conclusion. There are some interesting things to remind when we think about epistemic uncertainties. First, they are very, very often neglected, but they can be way larger than measurement errors that are usually taken into account. the second interesting point that is not so logical when you think about it, is that neglecting uncertainties leads to overconfidence in the predictions. That's what is illustrated here in this graphic. So you can see this is a profile across the fault. Here is a fault in gray. You can see some data that are in red here. You can see some predictions that are in orange and without accounting for uncertainties. So you can see that the predictions without uncertainties are very close to the data. And if you do account for uncertainties, then you can see that the predictions in green are very far, no, okay, not very, but are farther from the predictions than neglecting uncertainties. That is easily understandable by the fact that if you neglect uncertainties, then the predictions will compensate from the errors in the crustal structure. And the last interesting thing to remember is that the impact of our assumptions or the impact of the uncertainties will depend on the slip resolution. So it will depend on the distribution of the data, on the location of the data, and on the location of the slip as well. What I want to show, what I showed during my PhD, that accounting for uncertainties was really necessary to go towards more refined, realist, and robust deformation estimates. And I think when we are confident enough in our deformation estimates, we can start to compare these deformation estimates across several spatial and temporal scales. So that's what we try to do, for instance, with the L'Aquila earthquake that occurred 10 years ago in Italy. I'll just show you these results because I think that's nice. So we try to compare the strictly ecoseismic slip, so that occurs like just a few seconds during an earthquake, and then the early after slip that occurs 6 days after the earthquake. So here you can see the ecoseismic slip, which is in yellow to red, and the after slip, which is in blue. On the left, this is without accounting for epistemic uncertainties in the fault geometry or crustal structure, and in the right, it is accounting for everything. And what you can see is that these two slip models are very different. And I think this is another example to show you that accounting for uncertainties is very important. Another thing what we did, and I want to present you very quickly again, is to study the East Anatolian fault case, also accounting for uncertainties. So the East Anatolian fault accommodates the deformation between the Anatolian plate and the Arabian plate. So it all started with a work from Quentin, Olivier, and Jean-Mathieu, who determined the interseismic slip deficit along the East Anatolian fault. So that's what you can see here in purple. So 1 year ago, a large earthquake occurred in the East Anatolian fault, so the Elazig earthquake. So it's a magnitude 6.8, and it's the largest earthquake to have occurred on this fault over the last century. So that was pretty interesting. And I think it was a very good opportunity to do what I just suggested before, that is to compare our estimates of fault deformation across several temporal and spatial scales. So to make this comparison, we had first to estimate the slip that occurred during the Elazig earthquake. To do that, we selected the relatively complex fault geometry that you can see here with two main bands. So this geometry has been chosen because it will explain surface rupture and the aftershock locations. It has been, so the slip on the fault has been constrained by ESR data and GPS, some of them that you can see here. And at the end, what we obtain is a slip model for this earthquake. I will not extend too much on the description of this slip model, but what is very important is that to notice is that the slip actually well correlates with the geometry we have chosen. And in particular, what's very interesting is that there is absolutely no slip that has been imaged around the main bend of the fault. And this slip is actually very well constrained. That's what you can see here. So I think that's very interesting. And this is even more interesting if you change the fault geometry that you assume to find this model. So anyways, what we do in this case, we assume a planar fault geometry and we neglect all of the uncertainties. And what you can see is that actually do image slip around the main band in this case? So I think that was quite interesting. Next thing we can do is to compare this coseismic slip model to the interseismic slip deficit that has been inferred by Quentin and to the historical earthquake or the historical ruptures over the last century. So that's what you can see here. In A, you have a map view of the East Anatolian fault. So here is a fault that ruptured during the last earthquake. And in purple, you have the shallow interseismic coupling. In B, you have the extent of the historical ruptures that is shown. So here, rupture from the last century, here as well, and here the last big earthquake that occurred 40 years ago. No, 50 years ago, sorry. In C, you can see a view in depth of the interseismic coupling of the rupture of the elastic earthquake and of the rupture of an earthquake that occurred 10 years ago. So what's interesting to notice here is that you can divide the East Anatolian fault in three main segments. These three main segments are can be noted as highly coupled zones that are denoted into light purple hills, so the Butterworth segment and the West Palu segment and the East Palu segment. What's interesting to notice is that the Butterworth segment has been ruptured by the elastic earthquake, so that occurred last year, and that the portion of the East Palu segment, portion of the East Anatolian fault, also seem to have been ruptured by an earthquake 10 years ago. We could have stayed like, we could have kept our interpretation here, but what's interesting when using Bayesian sampling methods, and what's interesting to do when we are confident into our slip estimates is to go deeper into the comparisons. So that's what we did. And we wanted to compare the energy that was released by all of these earthquakes and the energy that was accumulated, on the Eastern Natural fault since the last historical rupture. So that's what you can see here. So in this case, we compare the moments that have been released or accumulated. If we look at the segment affected by the elastic earthquake, you can see that the moment released by the event is way larger than the moments that have been accumulated since the last historical rupture. So the first thing to say is that this historical rupture probably did not rupture, this portion of the East Anatolian fault, and that the elastic earthquake actually ruptured the seismic cap. The other interesting thing that we can notice is on the East Palu segment, you can see that the moment released by the 2010 earthquake is very, very close to the moment accumulated from the last historical rupture to 2010. What this means is that this rupture, this historical rupture, probably also ruptured this East Palu segment, and that this earthquake probably released all of the moments that was accumulated on the fault. Finally, if we look at the central portion of the East Anatolian fault, you can see that the moment accumulated since the last historical rupture of 1875 corresponds to moment magnitude of 6.6. So if this central portion is going to rupture, it may produce a relatively large earthquake. So this is a nice example of a very recent study, and I think this is what we need to go towards. So if we account for uncertainties, we will be able to be more confident into our results, and we'll be able to do very nice comparisons. That's also the interest of using Bayesian methods. If you have access to the posterior uncertainties, then you can also be confident into your interpretations because you take into account the uncertainties. There is one thing you may have remarked into for all of the earthquakes I presented before. It's that the Ridgecrest earthquake, the L'Aquila earthquake, and the Elastic earthquake are all continental earthquakes. And when you look at the continental crust, you can think that finally these approximations that we make, so planar fault geometry or a layered crustal structure, are not so big approximations and are actually a very or relatively good estimate of what the crust should be. What's interesting is that even if this approximation is not so big, the impact of this approximation can be very large. So this is quite annoying when you consider that there is another place on Earth where these approximations are totally wrong, and we know that, and we still persist in making these same approximations. This place I'm thinking of are subduction zones. So we all know that they are characterized by a very, very complex 3D architecture. So there is a large topography, the faults aren't planar, and the crust is very heterogeneous in 3D dimension, in 3 dimensions, sorry. What is very interesting is that this complexity is very often neglected. For instance, if you look at the sleep models that have been published by, for the 2011 Tohoku earthquake, so there have been more than 50 sleep models that have been published. I haven't looked at all of them, but I found only 4 that consider the 3D complexity for all of their datasets. So I think that's quite striking. The main reason for that is that it's very computationally demanding to account for such complexity. So very often it's just easier to make very strong approximation about the Earth structure. So in the following part of the talk, I will focus on 2 complexities: the topography, mostly in subduction zones, and also the 3D crustal structure. So let's go for topography. So what you can see in this image is the bathymetry of the Mariana Trench. So I think you all know that the Mariana Trench is the deepest trench in the world. What's interesting though is if you take the net topographic variation between the top of the volcano here to the bottom of the trench, then the distance is of 12 kilometers. And actually, if you look at the total net variation of topography for other subduction zones, then this distance also reaches 12 kilometers. That's what I want to show you here. So you have several topographic profiles which have been drawn across several migrate thrust ruptures. So in x-axis, you have the distance to the trench. In y, you have the topography. And each profile is color-coded by the net variation in topography. So the smallest variation is of 5 kilometers. That's already a lot. But the largest variations are of more than 12 kilometers. And this large variation especially occur in Chile, for instance. So the interest, I think, with topography, and that's what you can see here, is that it is widely known everywhere in the world. So if you account for topography, you do not need to take into account any uncertainty because we know it. So that's really nice. However, very often it is neglected because I said it is very computationally demanding to account for it. Very often you just need to do finite element simulations to take it into account. Also, so because of that, even if it's widely known everywhere, it has been neglected for almost all of these studies concerning co-seismic slip, or even post-seismic or interseismic slip. We started to study topography because Théa Ragon published a study 2 years ago where she compared the effect of topography alone to the effect of the 3D crustal structure alone. That's what I forgot to say actually. When topography is not neglected, very often its effect is mixed with the one of 3D crustal structure. And very often we just think that the combined effect is due to the 3D crustal structure alone, but actually Théa Ragon showed that it's not true. That's what you can see here. So she studied the Gorkha earthquake, so that occurred in Nepal. So you have the Himalayas. So it's a rather big topography. She calculated the surface displacement, accounting for topography or neglecting topography. And you can see the difference between the surface displacement here. And she did the same with a 3D medium or without a 3D medium. And what you can see is that the impact of topography alone is larger than the impact of 3D medium alone. For instance, here it reaches 40 centimeters, so that's quite a lot. So we were wondering after seeing this result, like, would this impact be as large for co-seismic slip models, or even for post-seismic or interseismic slip models. The other thing we wanted to investigate was if there were a method to take into account this topography, but without using very computationally demanding techniques. This method actually exists. It has been published 20 years ago by Charles Williams and Jeff Watch. And what they propose is to separate the effects of topography into two effects. The first one is related to the distance between the receiver, so the data, and the source, so the fault. And the second one is related to the effect of the shape of the topography, so the gradients. The methodology they propose is to account for the distance between the receiver and the source. To do that, you simply have to shift or to modify the depth of the source. So that's what is represented here. Just have to modify the depth of the fault, and then you can account for one of the effects of topography. So we wanted to investigate if this receiver elevation correction was sufficient to account for topography in our slip models. Because if it is sufficient, that's very interesting, and that's a very easy method to implement. So what we did was to investigate two case studies, the Gorkha earthquakes that occurred in Nepal 6 years ago, and the Maoli earthquakes that occurred in Chile 11 years ago. What was interesting by studying these two earthquakes is that they are relatively different. In Nepal, this is a continental earthquake. The fault is really, really shallow, and we have a lot of data, so the slip is very well constrained. In Chile, this is a subduction zone. We don't have many data, and the slip is not so well constrained, especially at the trench. What's also interesting is that the net topographic variations for these two earthquakes is very similar. It's about 6 kilometers. But you can see that the shape of the topography is very different. So what we started to do was to perform some synthetic tests. So the idea is to define a target slip model to calculate the displacement that is provoked at the surface by this slip model. We calculate the displacement at the surface accounting for topography. And then what we do is to try to retrieve this slip model, but either neglecting topography, that's what you can see here, using the receiver elevation correction, that's what you can see here, or just accounting for topography. So of course, if we account for topography, that's really good. If we neglect topography, then where the topography is larger, so that's here, the slip model is less well retrieved. The interesting point here, what I want you to remember, is that when you use the receiver elevation correction, then the slip estimates are pretty good. So this is very interesting because that means that in the Gorkha case, so where the fault is really shallow and where you have a lot of data, so where the slip is very well constrained, then the receiver elevation correction is sufficient. So it's a very nice result. If we now look at the Maoli case, so very different because the fault is deeper and we have far less data, so the slip is less well resolved. The results are, again, really different. So here you see target slip model. So you have two main slip patches at the trench. You can see that if you neglect topography, so that's here, or if you only account for the distance between the distance between the source and the receivers, then that's not sufficient to account for the effect of topography. You can see that we are not able to retrieve the target slip model at all. However, if we account for topography, the result is not perfect yet. You can see that indeed we image where the slip is larger, but at the trench we have some resolution issues and we are not able to infer the minimum slip values. What's interesting is also that these large slip values and wrong slip values are also affected by a large posterior uncertainty. So in the end, this model is far better than the other that we obtain without topography. What's to retain here is that at the trench, the shape of the topographic surface plays a key role, and that's why we are not able to image the slip properly. If we look at the results for the earthquake. So we are not looking at target sleep models anymore or static tests anymore. So you have the results without accounting for topographies that are on the left side here and on the right side here. You can see that these two ones are quite similar. So that's similar to the test I presented just before. And if you look at the results accounting for topography, then you can see that they are really different. For instance, at the trench, we have less sleep that have been inferred and in different location. Even deeper, we have larger sleep and in a different location, etc. I won't extend on these results because the idea was not to have a very robust image of the Maoli earthquake, but just to show the impact of topography. And finally, what we can say is that topography has a very large impact, especially in subduction zones. And this impact is true even for geodetic data only. That's something very interesting. And I forgot to say that it's very often topography studies when you studied when you use seismic data, but when you use geodetic data only, it's like almost often neglected. Here we show that it's very important to take into account even when we use geodetic data only. And one important thing is that it should be accounting for in almost any case. As I told you, the Gorka case is very specific with a very shallow fault and very good data. We are not sure it is representative of other earthquakes. In contrast, Morley seems far more realistic, and we show that topography really has a large impact. So the issue with this study was that, as I said, we only studied 2 events, and that's very hard to draw more generic conclusions about the topography from these 2 events only. So what we decided to do now is to investigate more generic cases to find if there are some specific geomorphic features that tell us that we need to account for topography or else encounter very large biases into our sleep models. So what we are currently doing is to design a set of generic synthetic cases. The first step was to design a generic topographic profile. So that what you can see here in orange, actually this profile can be is characterized by 5 parameters: the depth of the trench, the height of the forearc, the width of the forearc, the height of the volcanic arc, and the width of the volcanic arc. The idea is to look at the interplay between these parameters and also between the fault geometry, the slip resolution, and the slip location on the fault. And the idea would be to provide some generic guidelines on when and where we need to account for topography, so that, I don't know, we can just be certain that topography is needed or not when you try to solve for coseismic slip. I wanted to show some preliminary results, but they are too preliminary, so we'll just go towards the next part of this slide, of this talk, sorry. I talked a lot about topography, and I explained why I wanted to investigate topography alone, but I think 3D crustal heterogeneities are very important as well. There is a very nice tomographic picture that have been published recently by Stefano Berto and Lorcenini. So this is in Ankai through, and we give you an idea. The Moho here is like 15 kilometers depth. So I think we all know that elastic structure of the Earth is very complex. We also all know that this structure needs to be accounted for when we are studying the deformation on the faults. However, very similarly to the topography, we generally do not account for this structure because it's too computationally complex. What I will try to show you here is that we need to account for this structure, and we need also to account for the uncertainties of the fact that we consider them. We need to account for the uncertainties because we do not really know this elastic structure. We can image it, but as every image, it comes with a lot of uncertainties. So to account for the uncertainties of this structure, we use a very similar approach to what I presented just before and what I investigated during my PhD for the fault geometry and the layered crustal structure. To validate this methodology, we start by using very, very simple toy models. That toy model you can see here. So we look at infinitely long faults. So this is here. On this fault, there is a very simple dislocation that is uniform. We'll consider a dislocation of 10 meters, and you have a perpendicular profile with a lot of data points on it. So all of the toy models we investigate here, we have tried to solve them analytically, just for simplicity and because it is way faster than designing finite element simulations. The issue with that is that we have to make some approximations. These approximations are very good for what we want to do here, so that's nice. And these approximations are derived from the moduli perturbation approach. So what we approximate is that when you have a complex crystal structure with several interfaces, then you can just superpose two dislocations that occur in more simple crystal structures, with just one interface. So that's what you can see here. Let's go to the results directly. So the idea here is to consider a complex crust, so with different interfaces. That's what you can see here. You have the fault, a vertical fault here, and you have two gradients of velocities or shear moduli on either side of the fault. With this crystal structure, we calculate the surface displacement at along this profile at every data point. We add noise to the measures, and then we try to infer the slip or the dislocation on the fault using different crystal structures. So if we use the same crystal structure that has been used to estimate the surface displacement, that's what is here, then we end up with a nice result. So what you can see in this picture here is on the x-axis, the slip. So you can see that 10 here is the value of the dislocation that we use. So that's the value we want to infer back. In the y-axis, we have the depth. So as the fault is infinite, there is only one subfault per depth. And so you are estimating one slip parameter per depth. The blue rectangle here corresponds to the average value that has been inferred. So if it's around 10, then you are really correct into your estimation. The other colors that you can see here, that's more transparent, corresponds to all of the possible models that have been inferred by our inversion. So it's kind of the posterior uncertainty on every parameter for every depth. So again, if we consider a very complex structure and assume the same structure to make our inversion, then we end up with a very nice sleep model that fits the target very well. On the other side, if we invert this sleep model but assuming homogeneous crust, that's the case here, then you can see that we are not able to fit the target model at all. There are only two subfaults on which the target model is within the possible sleep models, but actually that's very bad. In contrast, if we account for uncertainties, so that's what you can see here, then the sleep model is actually pretty good. That's not as perfect as with the true structure, but that's quite logical. The way we account for uncertainties is slightly different than from the fault geometry, actually. In this case, we investigate the sensitivity of the surface displacement for every domain. So for instance, for the white domain here, we calculate one set of uncertainty, and for the black domain here, we calculate one set of uncertainties as well. So we calculate actually 6 sets of uncertainties, and we merged all of these uncertainties before introducing them into our inverse programs. I will present you some other interesting results. So in this case, we have a more complex crystal structure where we have two different gradients on either side of the fault. Again, if we use a homogeneous crust to solve for the dislocation, then you can see that we are not able to infer the slip at all. However, if you account for uncertainties, then the results are really improved. What's interesting is when you account for a more realistic crust. So in this case, we take as our approximation the average of the true crustal structure. In this case, the inferred sleep model with uncertainties is really, really good, even better than in the homogeneous case. So I think what's important to notice here is that it's better to use a very simple fold geometry, but accounting for uncertainties, so that's this model here, than to have a very realistic structure, but without accounting for uncertainties. That's what you can see here. And the best results are obtained if you use both very realistic structure and if you account for uncertainties. That's what you can see here. You can also do some tests in 3D, so that's what we did here. You have a map view of the fault here. So this is a strike slip finite fault, and you have an analog strike interface between the two faults. The ratio in chemodry between the two faults is of 0.6. And what you assume is that this ratio is of 0.9, so that actually the two sides of the fault are far more similar than what they are in reality. Again, what we obtain is that, sorry, I forgot to mention that the target model, so what we want to obtain is a slip within these orange squares here. So again, if we neglect uncertainties, that's what's shown here, the result is pretty bad. And if we account for uncertainties, and again, the result is improved. We can do the same with a strike perpendicular interface. That's less realistic, but I think that's a good illustration of along strike variations that you can find in reality. Again, if you neglect uncertainties, results are very bad. And if you account for uncertainties, results are very good. What I want you to remember here is that what is very interesting is that in this case, even if the B side of the fault, so that's the right side of the fault, is wrong, the A side of the fault, so that's the left side of the fault, is always true because the crustal structure we assume is similar to the true one. And even if it's true, if we do not account for the uncertainties, then the slip that we estimate on this correct side is totally wrong. So this means that even if you think that your crustal structure is quite realistic in one particular location, if it's wrong in another place, then it can totally bias every estimate. So finally, what we showed in this study was that the 3D uncertainties can be accounted for, at least it's working well for very simple cases. We need to account for every type of uncertainty, that's what I was just saying. And what I was just saying before as well is that we really need to account for uncertainties, but also to use very realistic estimates of the crust. That's the main conclusion of my talk. Yes, we can hamper the effect of our approximations in sleep estimates, and to hamper these effects, we have to do two things. First, it's to account for uncertainties, so to account for the imperfections of what we don't know, and the second thing is to build realistic replicates of what we actually know or what we think we know. To finish, I just want to illustrate some perspectives and just to show that to explain what I'm working on right now. So I think it's important to investigate the impact of these 3D uncertainties and our ability to account for it in for real cases and for real structures, so far more complex. That's what I'm doing right now. I think one of the main questions we may be able to resolve while doing it is how well and how deep do we resolve the deformation near the trench, while showing you some results for the Maoli earthquake. And I think the problem of resolution near the trench is very important, and it's very important for both coseismic slip estimates, but also for interseismic coupling estimates, especially in subduction zones. And finally, so that's why I'm asking this question. I think we can wonder, how do these heterogeneities affect our estimates of aseismic deformation? Even if for coseismic slips, these kind of uncertainties are very often neglected, sometimes they are actually taken into account. But when we look at the aseismic deformation estimates, so interseismic coupling or slip deficit estimates, then in this case, they are like almost always neglected. And when we look at the impact of these uncertainties in co-seismic slip models, we can wonder what will be the effect on this kind of models. That's all. Thank you for listening to me, and I hope it was not too long.